All right, so this is a continuation of section 10.2, which we're talking about series. So in class, we finished talking about geometric series and we went through a couple of examples. Now we're going to go over an example where we're talking about geometric series and we're going to explain why repeating decimals represent rational numbers using the idea we just learned. Okay, so jumping right in, we want to write the number 5.2323 repeated as a ratio of integers. So, doing that, use blue, 5.23 repeated is the same thing as 5 plus 23 over 100 plus 23 over 100 squared, and we can write plus 23 over 100 cubed, and so on. So what's the thing to note? After the first term, we have a geometric series. We have a geometric series where our A is equal to 23 over 100 and R is equal to 1 over 100. So notice that we didn't pay attention to the first term. So one other thing to note is that the absolute value of R is equal to 1 over 100, which is less than 1. So in fact, we know this series is going to converge. So what can we say? We can say that 5, draw a bar here to let you know we're writing something else. So 5.23 repeated is the same thing as 5 plus, since we know that after 5, this part is a geometric series, and we know what A is and we know what R is, we can write its sum. So we know that it's 5 plus 23 over 100 divided by 1 minus 1 over 100. And that's what we get because it's A divided by 1 minus R. So that's equal to 5 plus 23 over 100 times 100 over 99, because that's the reciprocal of the denominator. So that's equal to 5 plus 23 over 99, which you can find the common denominator, simplify, and you get 518 divided by 99. So we use what we just learned about geometric series to take this decimal and write it as a rational number. Now, does this series, the sum n equals 1 to infinity of minus 1 to the n plus 1, does this converge or does it diverge? Well, let's write out a sequence to see what happens. So S1 is just equal to negative 1 squared, which is equal to 1. So what we did was we plugged n equals 1 in here to see what we got. Now, remember, S2 would then be equal to negative 1 squared plus negative 1 cubed, because now our n is equal, we're going from n equals 1 to 2. So we plug it in, we get this plus this, and that is equal to 1 minus 1, which is 0. Now S3 is equal to negative 1 squared plus negative 1 cubed plus negative 1 to the fourth power, which is equal to 1 minus 1 plus 1 equals 1. Well, what's going to happen? When we continue to look at the partial sums, they alternate. So the partial sums that we're looking at alternate between 1 and 0. Therefore, the series diverges. Therefore, the series diverges. Okay, so that's something to remember. So what's the purpose of even talking about this particular example? Because we want to know that there are other series than the geometric series with the absolute value of r greater than or equal to 1 that actually diverges. So keep that in mind. Okay? Now, let's talk about the telescoping series. The telescoping series, you want to keep in mind of a telescope that looks like this at the bottom. And because the name telescoping series actually comes from what the picture of a telescope looks like, because it collapses like an old hand telescope into something like this. Now, what we're going to do is we're going to find the sum of the series, the sum where n ranges from 1 to infinity of 1 over n times n plus 1. So our solution, first note that this is not a geometric series. Okay, this is not a geometric series. So we need to look for a pattern in the partial sums. So let's look at the partial sum, Sn, which is the sum where I ranges from 1 to n of 1 divided by I times I plus 1. That's equal to, if we expand it, so you can get a better look at it, it's equal to 1 over 1 times 2. That's what we get when I is 1, plus 1 over 2 times 3, plus 1 over 3 times 4, plus everything out to 1 over n times n plus 1. Okay? Now, remembering partial fraction decomposition, so recall partial fraction decomposition, we get the following. 1 over I times I plus 1 is equal to 1 over I minus 1 over I plus 1. So if you recall, whenever you use partial fraction decomposition, you would write A over I minus B over I plus 1, and then you'd have to find out what A and B were. So it turns out you get 1 and negative 1 here. So what that allows us to say from this point is that our partial sum is equal to the sum where I ranges from 1 to n, and because we just found out via partial fraction decomposition that we have that equality here, we can write that the partial sum is equal to the sum where I ranges from 1 to n of 1 over I minus 1 over I plus 1. Now, that means that if we expand it, when I is equal to 1, we get 1 minus 1/2. When I is equal to 2, you add I is equal to 2, you get 1/2 minus 1/3. Then when I is equal to 3, you get 1/3 minus 1/4. And you keep expanding it until you get to your last term. You'll have plus 1 over n minus 1 over n plus 1. Now, what happens here? Well, the 1/2 will cancel, the 1/3 will cancel, and then your 1/4 will cancel, and then everything will cancel. This 1/9 is going to cancel with the terms before, and then you're going to end up with, when you simplify it, 1 minus 1 over n plus 1. So it collapses. That's why it's called a telescoping series. So now we want to find the sum of the series. That's what our goal is. So now we need to make sure we evaluate the limit of the partial sum as n approaches infinity. That's equal to the limit as n approaches infinity of 1 minus 1 over n plus 1. And as n approaches infinity, 1 over n plus 1 approaches 0. So we get 1 minus 0, which is just 1. So the series converges and its sum is 1. Okay, so the series converges and its sum is 1. So that's a telescoping series. If you need to pause the video, rewatch the idea. It's very important that you understand these. So now, page 7, we are going to discuss some theorems and some results. The first theorem says that if the series, the sum of an, where n ranges from 1 to infinity, if that is convergent, then the limit of an as n approaches infinity is equal to 0. So if you have a convergent series, then the limit of that sequence an as n approaches infinity is equal to 0. Some things to note. If the sum, or if this series is convergent, then the limit of the partial sum as n approaches infinity is equal to s, and the limit of an, that original sequence as n approaches infinity, is equal to 0. The converse of this theorem is not true. So in other words, if we look at the limit of a sub n as n approaches infinity if that equals 0, then we cannot conclude that the series is convergent. That's what 2 says. Now, a test for divergence, which follows from the theorem above, says that if the limit of an as n approaches infinity does not exist, or if the limit of a sub n as n approaches infinity is not 0, then the series is divergent. This is an excellent thing to remember, and you will need to know how to apply it as well. So let's see how the test for divergence works. We want to, in this example, show that this series, the sum where n ranges from 1 to infinity of n divided by 2n plus 5, we want to show that that diverges. So this test for divergence here suggests that we should look at the limit of an as n approaches infinity. Well, that's the limit as n approaches infinity of n divided by 2n plus 5. Remember your rules for limits. This is the limit as n approaches infinity. You can divide everything by n, so that's the same thing as n over n divided by 2 plus 5 over n, and that's equal to 1/2. Or in other words, let's write a step before that. Erase this. That's equal to the limit as n approaches infinity of 1 divided by 2 plus 5 over n. And as n approaches infinity here, as n approaches infinity, 5 over n approaches 0, and we actually get 1/2. But what does that mean? Well, if we go back up to the theorem, the test for divergence, it said if this limit does not exist, or we're not in the case where our limit does not exist, or if the limit is non-zero, oh, we're in that part. We got 1/2. That's not equal to 0. Since that's not equal to 0, that means that this series that we looked at, that means it diverges. So that's not equal to 0. Therefore, the series diverges by the test for divergence. Make sure you know how to apply that. And what we're going to end with is some more information about helping you determine whether you have a divergent or convergent series. So, note, if the limit of the sequence an as n approaches infinity is not 0, then the series is divergent. If you have a non-zero limit of a sequence, then your series is divergent. If the limit of your sequence is equal to 0, as n approaches infinity, we can't conclude anything. We don't know anything about the series. You only know something about the series if the limit is non-zero. Okay? A theorem. Convergent series play nice with constants, sums, and differences. So we're going to suppose C is a constant, and we're going to suppose that the series A sub n and the series B sub n are convergent. Then the following are also convergent. The sum of the series C A sub n is equal to C times the series A sub n. So in other words, the constant can come out. If you have a series of a sum, that's equal to the sum of the series. If you have a series of a difference, that's equal to the difference of the series. So now we will look at one final example for this section. So if we want to find out what happens with this series given here, we have the series where n ranges from 1 to infinity of 3 to the n minus 1 divided by 6 raised to the n minus 1. So first things first, I would suggest rewriting it. We have here a difference. So we can rewrite this as the sum where n ranges from 1 to infinity, and remember we don't have to write that all the time, of 3 raised to the n minus 1 divided by 6 to the n minus 1 minus 1 over 6 to the n minus 1. Well, great, because now we have a series of a difference. Well, we just learned in the theorem above, part 3, that that's equal to the sum of 3 to the n minus 1 divided by 6 to the n minus 1 minus the sum of 1 over 6 to the n minus 1. That's equal to the sum of 3 over 6 to the n minus 1 minus the sum of 1/6 to the n minus 1. That's equal to the sum of 1/2 to the n minus 1 minus the sum of 1/6 to the n minus 1, which means you have two geometric series where r is the absolute value of r. In this case, r is 1/2. This case, r is 1/6. They're both less than 1, so they both converge. So you can say this is equal to a in your first series is 1. So this is equal to 1 over 1 minus 1/2 minus 1 over 1 minus 1/6. And this is equal to, running out of room, so I'll go up here. That's equal to 1 over 1/2 minus 1 over 5/6, which is equal to 2 minus 6/5, or in other words, simplify, you get 4/5. So you found out that our original series here converges to 4/5. So one thing to note, and this is to end with, adding or deleting a finite number of terms to a series does not alter the convergence or divergence. The sum will probably be different, but the result will not be different. If your series converges, it's going to converge. If it diverges, it's going to diverge, no matter whether you add or delete terms. One last thing I want to end with is just make sure that you are comfortable with your algebra. Remember, a to the n over b to the n is equal to a over b to the n. That's extremely useful. And that ends section 10.2, which is series.